Hello, my name is Adam Botach. I'm a master's student at the Technion Institute of Technology in Israel. In this video, I'm going to present my master's thesis paper, End-to-End Referring Video Object Segmentation with Multimodal Transformers. We are interested in solving the Referring Video Object Segmentation task, or RVS. The goal of the task is to segment a text-referred object instance in the frames of a given video. To illustrate, in the following example, the query reads a hand giving a yellow ball to a dog, and the expected output is a set of per-frame segmentation maps for the hand. We know that in RVS, the text query may describe the object of interest either by its appearance or by the action it is involved with. Due to the complex nature of this multimodal task, which combines text reasoning, video understanding, instance segmentation, and tracking, existing approaches typically rely on sophisticated pipelines in order to tackle it. In contrast, here we propose a simple end-to-end transformer-based approach to RVS, which significantly outperforms existing RVS approaches. We call our method the Multimodal Tracking Transformer, or MTTR. To accomplish this, we employ a single multimodal transformer and model the task as a sequence prediction problem. Given a video and a text query, our model generates a set of instance sequences for all objects in the video. Each instance sequence is a sequence of embeddings that can attend to a single object throughout the video. To illustrate this, in this example, the sequence of blue rectangles attends to the hand, while the sequence of the green circles attends to the dog. Finally, the model determines which instance sequence attends to the text-referred object and returns a sequence of segmentation masks that corresponds to it. MTTR's pipeline consists of four main steps. In the first step, we extract visual and linguistic features from the video and text. For the video, we use a spatiotemporal feature encoder. This encoder outputs per-frame feature maps, which contain both appearance characteristics and action semantics. Similarly, a transformer-based text encoder is used to extract linguistic representations from the text. Then, features of each frame are flattened, summed with two-dimensional positional encodings, and concatenated with the text embeddings. This results in a set of multimodal sequences, one per frame. In the second step, the resulting sequences are fed into a multimodal transformer. The transformer architecture we employ is similar to the one that was originally proposed in DTR for object detection purposes. In the encoder layers, the textual embedding exchange information with the visual features of each frame. Then, the decoder layers, which are fed with the outputs of the encoder and a set of object queries per input frame, query the multimodal sequences for entity-related information and store it in the object queries. We note that corresponding object queries of different frames, like the set of blue rectangles on the right, are represented by the same unique color and shape, belong to the same instance sequence, are trained to attend to the same instance in the video, and share the same trainable weights. This design allows for natural tracking of each instance in the video. Step 3. In this step, for each instance sequence, we predict a corresponding sequence of segmentation masks and a corresponding sequence of reference scores. A high reference score for an instance in a frame indicates both a strong text correlation and the visibility of that instance in the frame. Step 4. In the final step of the pipeline during training, the predicted sequences are matched with the ground truth sequences for supervision. The matching process is based on the Hungarian algorithm, while the matching cost function operates per time step and considers both reference and mask compatibility. Then, after an optimal matching is found, the whole pipeline is optimized end-to-end. Finally, during inference, we need to determine which of the predicted sequences is most strongly associated with the text. In this example, is it the blue square sequence, the green circle sequence, or perhaps some other sequence? For this, MTTR employs a novel reasoning scheme called the temporal segment voting scheme. This scheme grades each instance sequence based on the total association of its terms with the text. Finally, the segmentation mask sequence corresponding to the instance sequence with the highest score is returned. This scheme allows our model to focus on more relevant parts of the video with regards to the text when making its decision. To evaluate our approach, we conduct experiments on 3 RVS benchmark datasets. On A2D sentences and JHMDB sentences, the two most popular RVS benchmarks, MTTR significantly outperforms existing methods across all metrics. Additionally, MTTR also delivers strong results on Refer YouTube VOS, a newer, larger, and more challenging RVS dataset. To read our paper, gain access to our code, or try MTTR by yourself using our interactive demos, scan the following QR code. Thank you for your interest in our work.